Okay, welcome. So we're going to go on today with convolution and how that relates to Fourier series, as well as how useful it actually is. It's one of the most, far-reaching theorems that they got with respect to Fourier series, and it helps to make us to make very clean, crisp images where we otherwise would not. And it has helped people in astronomy to get rid of a multi-billion rand embarrassment in the Hubble Space Telescope. Okay, so just to go back to the example we did at the end of the previous lecture, we defined the convolution of two functions. Let me just get the focus of this thing. That's better. Okay, simply as this integral, it goes from minus infinity to infinity. The first function's argument is s, f's argument is s, and g's argument is x minus s. So what you've done, you've taken g, you've flipped it over, and you're moving it about. Okay, and then s is your integration variable. So that's the definition of convolution. And then we did the example where you had f was one box function, and g was another function. And then to work out the convolution, what we did was simply to look at what g of x minus s is. We had to evaluate that. And because it was an inequality, we simply said that was equals to a half if x minus s is less than or equals to 1 and greater than 0. And if you manipulated that so that you had s as the principal argument, because you're integrating over s, you had that's equals to a half if s lies between x and x minus 1. Okay, and then we had that for different x values, right, because x is now in some sense the thing that comes out, your little box g of s lay at different spots while this f of s remained constant. So f of s doesn't change, and generally if f is a more complicated function, I try and choose the one that's more complicated as the one that doesn't change. And g of x minus s varies as x varies. So if g of x minus s is there, it's non-zero between x and x minus 1. If it lies over here, this product of the two is 0. Okay, but we can move it until eventually over here, where it overlaps with this other function, the product of f times g is then got a non-zero property. And we can rewrite this integral if you want to get it out. First, it's the integral of f of s times g of x minus s. But we now see that g is non-zero only where s lies between x and x minus 1. So we can say that this integral is equivalent to a half, right, because g is a half. The integral between x and x minus 1 of f of s. Okay, and so if x lies over here so that x and x minus 1 doesn't overlap with f of s, the integral is 0. Over here, where this box does overlap with f of s, the integral you have starts from this point over here and is the product of everything inside here with f. So what you have, in other words, you then want this little bit to be your integral. And if you then write it out, what you get is the full expression is g, the convolution of the integral of x minus 1 to x is simply 0 if x is less than 0, in other words, in this region. If x lies between 0 and 1, in other words, if this leading edge intrudes on your function, then what you have is you're going to integrate s from 0 over here to the leading edge of x. And what you're going to be integrating is the function, which is just 1 times the half that comes from g. So the answer is simply going to be s over 2 evaluated at 0, the one boundary, and evaluated at x, the second boundary inside of here. If x gets bigger, in other words, this leading edge goes out over there, you're going to have this situation where you have this box has moved past, and you're going to need to integrate from this line all the way to 1. In other words, you can integrate from x minus 1 all the way to 1. Okay, and you're just going to put it in your integral and evaluate it. And then finally, when this box leaves, you're going to have 0. Okay, and so you can literally evaluate these boundaries in here, and what you get then is the thing we derived, that the convolution of f star g is simply a function that looks like that. In other words, between 0 and 1, g is simply a half x, and between 1 and 2, g is 1 minus x minus 1, so 2 minus x over 2, and this is what this one is. Okay, so just another example of how to work out the convolution, and I've posted the problem set so you'll have your own opportunity with this week as well. Right, so why is this important? The reason is convolution in the physical space is quite complicated. It tends to smooth the function, but especially if the functions get more complicated, you're basically doing an integral, and it's not always an easy integral to do, especially if both f and g actually depend on they have a shape. In other words, they can be any functions. So, but there's an easier way of doing it, or there's a very good relationship between convolution and Fourier integral. So the convolution theorem is a theorem that governs how the Fourier transform of the convolution is related to the Fourier transforms of the individual functions. So the main thrust of the convolution theorem states basically that the Fourier transform of the convolution of two products, okay, is simply the product of their Fourier transforms, which makes things easier because in real space working out the convolution is hard. But if you happen to have the Fourier transforms of the functions involved, you just multiply them, and then you have the Fourier transform of the convolution, and then you can take the inverse Fourier transform to get this thing back. So it gives you a different way of actually working out the convolution between two functions. And this particular way is very, very useful whenever you're working with cameras or telescopes or anything that takes an image. And we use it a lot. And I'll tell you why by the end of the lecture. So it's quite a beautiful proof because it's just a direct application of our definitions of convolution and a Fourier transform. So I'm actually going to do it here. So you literally just write out what the definitions are. So the Fourier transform of the convolution of f with g is simply the definition of your Fourier transform. There you've put inside the convolution of f with g times e to the minus 2 pi I ux dx. So that's just our definition of our Fourier transform. So the next step is you write out what the convolution is. So the definition of our convolution is simply this integral from minus infinity to infinity, f of alpha gx minus alpha d alpha. And what you're going to do now is again what we've done in so many of these other proofs. One, you're going to swap the order of integration. So you can see we're integrating over d alpha and we're integrating over dx. So there's absolutely nothing that stops us from taking this integral sign all the way out over there. Then we've just got to take that d alpha all the way out over there. We're still integrating over everything. The next thing, if we do that, we can take this f alpha also on the outside because nothing inside of here then depends explicitly on x. So we can take it out of the integral with respect to x. And then the next thing we can do is we want to write this whole thing. We're aiming here. So we want to write it as a Fourier transform. And f of alpha is still kind of okay, but we're missing the definition of our Fourier transform. So we want an e to the alpha something. This g of x minus alpha is annoying because we actually want to take an integral over the argument of g to get the definition of the Fourier transform. So what we're going to do is start over here and change variables. Okay, so what we're going to do is we're going to say let t equals to x minus alpha. So that alleviates that problem. In other words, there's just an argument of g now. But the moment we say t is equals to x minus alpha, wherever we get x, okay, we're going to have to, because we're replacing x minus alpha with a new variable t, wherever x appears, we now have to replace it with t plus alpha. Okay, and the only other place besides this where x appears is over here. And that's actually a bonus because it gives us an alpha and an exponent that we were missing to make this thing a Fourier transform. Okay, so we've let t go on to x minus alpha, and that immediately means we replace x up here with a t plus alpha. And the other place where x appears is this dx. We've got to work out what that is, but that's easy because dx is simply dt. Just taking the differential of this expression while alpha remains constant gives you the fact that dx is equals to dt. So let's now go ahead and put all this stuff into our integral. So we once again have the Fourier transform of f convolved with g at x, and we then get this expression. So the first thing we've done, remember, was we all changed the order of integration. So we took the integral from minus infinity to infinity of f of alpha outside of here, and we put the alpha outside. And then we are left with the integral from minus infinity to infinity over x, but that's now going to be an integral from minus infinity to infinity over t. And we've replaced this g of x minus alpha with g of t. And our exponent, e to the minus 2 pi I x, is now e to the minus 2 pi I, ux is e to the minus 2 pi I u alpha plus t. Okay, so it's just a direct substitution in. Any questions at this stage? Yes?
Why do we have a
U comes from the definition of the Fourier transform. Okay. No, it's fine. It's good to, because it's f of u, we put the argument in our Fourier transform as f of u. So it was carried all the way down to over there. Okay. So now the next step is, if we go back to what our definition of a Fourier transform is, we want to get this alpha out of here, because then we actually have the perfect description of what the Fourier transform of g is. The way we get the alpha out of here is we simply write this e to the 2iu alpha plus t as the product of e to the 2ui alpha, minus 2ui alpha times e to the minus 2ui t. Okay, and we leave the t inside and we move the e to the 2ui to alpha out of the integral. So there we go, we've done it. So there we split this exponent into the e to the 2ui t part, and we took the e to the minus 2ui alpha part out of the integral. And what we now have is basically our definition of what the Fourier transform of g is, and we label it as such. Okay, so that everything in the bracket became the Fourier transform of g, and we're now left with this expression. We have the integral of f of alpha g of u e to the minus 2ui alpha. We're integrating over alpha, so g of u does not depend on alpha, so we can move it outside of the integral. Okay, and we are left with the integral, or the definition of the Fourier transform of f only. And so that basically concludes the theorem. A very beautiful theorem, very straightforward to prove, and you're going to see it's going to be immensely powerful. It's possibly the most used theorem in image processing you'll come across. It's also the thing that makes all the cameras on our smartphones possible. Okay, because the cameras on our smartphones don't always have very good lenses, and yet we get these fantastic images way better than we used to get with those old shooting cameras. And it's all in the software, okay? And this particular theorem plays a very large role in that. You can prove using this type of method of simply writing things out, changing the coordinates, and then recombining the terms. You can prove two other very similar theorems. The first one is, we've been having the expression for this convolution, and we wrote it like this, which looks somewhat asymmetric in f and g, but you can actually prove that the convolution of f star g is exactly the same of the convolution of g star f. Okay, and here you can basically see how you would go about doing that. Is you would do exactly the same trick. You would simply write down this definition of convolution, then you would go about changing your variables, okay, except you're not going to change, you're not going to set t equals to x minus alpha and then view t as a replacement of x. You're going to set t equals to x minus alpha and then view t as a replacement of alpha. Okay, and if you then do the change of variables, you're actually going to be able, or rather, you're going to be able to switch this integral that it looks exactly like g of some function times f of x minus that function. Right, so it's the same trick you're using to prove this. Another thing you can prove is that the Fourier transform is of the product of f and g is equals to the convolution of the Fourier transforms of f and g. To prove this, you're going to basically start with the convolution of the Fourier transforms and work out the inverse Fourier transform, and then go through exactly the same trick, except that this minus now becomes a plus. Okay, so all these theorems are related to this convolution theorem, and they are very, very useful to have. So if you make proofs, know that these things are here. For the guys that are just interested in the image processing part, know the tricks that you use to compute it, because one day you might come across a piece of software that's broken, that you want to get an image out very desperately, and you might actually want to start playing with this. And how you play with it, I'm going to look at in the next couple of lectures. So one step I'm going to do before I do that, because I find that the flow of the lecture is slightly better than the notes themselves, is we've now got the convolution theorem. That's nicely proved mathematically. I want to introduce another idea before I go to the actual practical application of the convolution theorem. And this thing is the idea of a Dirac Delta function. Okay? It's a very special function that is in some sense the identity of the convolution property. So if you have a Dirac Delta function, suppose f is equals to g, g is equals to delta, and you take the convolution of f with g, you're just going to get your function back. Okay, so it's the thing that if you convolve it with another function, it just gives the function back to you. Okay, it has some very beautiful properties that I'm now going to look at, and I'm going to look at its definition, and it's used a lot in image processing. The interesting thing is that it was developed by Dirac. He's a physicist, and he developed it as an approximation of a point charge that has got absolutely no extent. So when he was working with an electron, he wanted to find a way of mathematically representing the electron. And the thing he came up with was this Dirac delta. Well, I call it a function, the notes call it a function. Strictly speaking, it's not a function. Okay, it doesn't exist in the way a function does. The reason I call it a distribution is it behaves exactly like the function, provided for one thing, you've got to put it under an integral sign. You cannot view it all on its own very easily, because then you are going to make mistakes in calculation. So very important, it's a Dirac Delta distribution rather than a function. If you work with the properties I'm going to give you now, you're fine, but just know there's a difference between it and an actual real function. Okay, so we often call this delta of x, okay, and this is different from the delta. I've been using delta kn, which is the Kronecker delta function, which basically is 1 if k is equals to n and 0 otherwise. This is the distribution. We call it delta. We usually give it an argument of x. And what it does, it has the property that it behaves, okay, that as if it is infinity at x equals to 0 and 0 when x is not equals to 0. And in addition to that, it's got the constraint that even though it's infinity at one point, the actual integral of the function from minus infinity to infinity is always 1. So this is why it's not a real function. You can't actually get a function that behaves like this. You can get a series of functions that limit to this behavior. So this is the first property of our Dirac delta function. The second one is, if you take the convolution of the Dirac delta function with a function f, in other words, if you do this integral, what you are going to get back is the integral of f of x times the delta of x minus x0 is equals to f of x0. You're simply going to get the function back evaluated at this point of your function. The Dirac delta function is also symmetrical. If you put a minus inside of here, it's exactly the same. If you multiply the whole thing on the minus to get x0 minus x, which is your actual definition of convolution, it is the same thing. Right, so the Dirac delta is symmetrical, and this property of when you integrate from minus infinity to infinity of it with f of x, you just get the function back. And finally, just this thing rewritten is basically the convolution of f with any delta function will give you that function back. Okay, so Dirac delta was working with electromagnetism, a lot of radiation, a lot of electrons emitting it, and this is what he invented to do it elegantly. And he was a very, very elegant both physicist and a mathematician. Died very young, or not died very young. He was a strange guy. He was definitely on the spectrum, quite difficult to work with, very uncommunicative, but he was absolutely brilliant when it came to mathematics. Okay, so that's our distribution. Those are all the properties. And let's now basically see how we use it. In fact, see how it's often used in electromagnetism. So suppose you have not one of them, but three of them. So we have a delta function of x plus big T, a delta function of x, and a delta function of x minus big T. Okay? And often when we're working with these delta functions, we represent them as simply a straight line up and with an arrow on top, indicating that it actually goes to infinity. And if you noticed right on the beginning, when we did the sampling, where we did the discrete Fourier transform, I had a whole bunch of arrows going up. The answer is because you actually can use the Dirac delta function to write down the sampling of an image. But anyway, so suppose we have a Dirac delta function, three of them like this, we represent them this way graphically, and suppose we have a function f that we want to convolve this thing with. So we have property 3 that states to us the convolution of f with the Dirac delta function is simply the function itself, okay, evaluated at x. So if, f of x is equals to this thing, it's a, it has an amplitude a, and it has an extent little a. If we convolve this thing with our Dirac delta function, or with this function g, what we get out, we can calculate simply by using the definition. Here we have the definition of our convolution of f star g of x is simply the integral from minus infinity to infinity f of alpha g of x minus alpha d alpha. And so if we now substitute in g over here, okay, wherever g is, we replace it with this, and we replace x with x minus alpha, what we're going to get is the integral of minus infinity to infinity g of x plus t, okay, but remember I've got to replace x with x minus alpha, so minus alpha is the first term, plus the integral from minus infinity to infinity f of alpha g of x, which then here becomes x minus alpha. And the next one is the integral from minus infinity to infinity of f times the delta function of x minus alpha minus t. Okay, so here's what the integral definition is. Remember, we have this basically, just looking at this integral, we have the integral from minus infinity to infinity of f of x times the delta function of x minus x0 is simply the function at x0. So the only thing that's required now is to be clear about what x is, and in this case x is equals to alpha, and to be clear about what x0 is, and to remember that your delta function is even. In some sense, you can switch the sign without changing the outcome. So here we have, there's alpha, so this whole thing is x0, so this will give us f of x plus t. Here we have alpha, so this will give us f of x, and here we have alpha, so the rest is x0 over there, so this is x minus t, and what we get out is that we have f of x plus t plus f of x plus f of x minus t. Okay, so what convolving this f with this combination of Dirac delta functions actually did was make several copies of our function over here. Questions with this thing? Okay, I often think of the Dirac delta function as a gramophone needle. You know those old records that you have, that you had the gramophone going, you have like the record rotating and the needle coming down, and it goes up and down, and it makes gives out a current which the amplifier then amplifies. Very often a good way of viewing the Dirac delta function is simply as this needle, it goes about and it reads other functions and it can do things with them. And in this case, it says, here I basically made a function that is basically going to take whatever function you put in or convolve it with and give that function back, just positioned differently. Okay. Very, very useful. And we're going to see what that does when it comes to image convolution in a moment. Questions here? The Dirac delta function is very simple in definition, very non-obvious, obvious in some ways in the way it works. When you work with the Dirac delta function, be careful of this definition. Always go back to these other guys when you work with it. Okay, so as long as you're using these conditions in a calculation, you'll be totally fine. But don't think of it as a function. It's got to be inside an integral for it to be useful. Okay, so now let's look at our model, simple model of a camera. So some of the simplest models, some of the very first cameras, they called the camera obscura. I don't know if you know, there's an artist, Jan Vermeer, that did one of the first guys that did these super, super realistic images. And what he did was he cheated. He had a very, very thick curtain, and he was famous for his scenes in city life. He had a very, very thick, dark curtain in his studio. And what he did is he took a pin and he pricked a hole in it. And then through that hole, the scene from the street then was like a camera. It came in through the hole and it was projected onto a screen, and he used that to get a very fine detail and to put the detail into his painting. So he was actually, and they called that camera the camera obscura, or the pinhole camera, literally where you put the screen in front except for one tiny point, and then you got a scene, a street scene projected out. The scene was very dim, so it damaged his eyes, but he did get it on enough so that he can actually paint great detail, or the most detail people had seen up to that time, simply by using this camera obscura. Okay, so that's in some sense an idealized camera. He had to make that hole very, very small, otherwise he would get a blurry image. Okay, and so what we're going to do is I'm first going to sort of derive a little bit of the image in a very simplified model. Then I'm going to tell you it generalizes without deriving it. And then I'm going to tell you how we get back the sharp image. So the basically idea over here is you have two things. You have the real world, this function f of x, which is all the light intensity that is being emitted by the mountains and the trees and everything in the street. Okay, so we're going to call this basically this profile, and this is once again also just a 1D example, and we're actually going to start doing 2D examples when we work with the images, but this is just to get the idea. So you have f of x that gives us this light intensity, and then we have a camera over here, either a film or the retina of an eye or a CCD camera. Okay, and on this we then record the light that comes to our eye. Okay, so you have two things. You have the original image, that's the intensity of the light that is emitted. You have the image you've actually recorded, and you want to understand the relationship between them. Okay, and so in our very simple model, we're going to start, instead of having just like that camera obscura, we're going to put a barrier like a very thick curtain. Okay, and we're going to cut a hole in it, and this hole is not going to be a pinpoint like Vermeer did. We're just a bit clumsy with our scissors and we cut a bigger hole. And so what we now want to do is discover what we're actually measuring. Okay, typically to get a better image, the first hardware cameras used to put a lens in here and to focus the light, and we can do the same thing, and you can go through all the mathematics. In fact, many people have done so, but you will get back to the same result that I'm basically going to derive in a more understandable way now. Okay, so we've cut the hole, and as a result, the thing is that arrives here at the camera is going to be blurry and out of focus. And we eventually want to know is, even if we've got such a lousy camera, can we get back what the image should actually be? Okay, so this is the basic thing of image processing and image reconstruction, is how do you improve and get a better rendition from your image of what is actually happening in reality. Okay, so we're going to assume there's no lens, we're going to assume the camera's, and therefore the camera's out of focus. So our actual image is not f of x. In fact, if we look at this geometry over here, what we can see is, because this hole has a finite extent d, the light from the original picture, from A to B, all that light, the way we set it up, is actually going to be concentrated on that point. So this particular point over here is going to have the integrated light from x plus d to x minus d. And so just to get to that result, let's do some look at some of the geometry. Here's our angle theta 1, okay, and we want to simply write that down, and we've got the screen that blocks the light, and we've got the image. So let's just simply write these things down. So here, this distance over here is x minus a half d. So that's the basically the y argument over here, and this distance over here is d. Okay, so that's tan of theta 1 when we look solely at the smaller triangle. If we now look at the bigger triangle to connect it to the image, what we're going to have is that is BC over 2D. Okay, so that's the base over there. And from that expression, we can immediately get an expression for what BC is. In other words, what part of the image we are actually taking the photograph of, or the earliest part of the light from the image that can actually contribute over here. It's simply 2x minus d. And we can do the same thing with this other angle that goes to the other opening side of the image. We can say that tan of theta 2, in other ways theta 2 is over here, is simply x plus, so x goes from there to there, plus a half d over d. And we're going to say that's equals to, here on the actual image, it's the distance AC over 2d. Okay, so that's just the geometry of the image, and eventually it gives us that AC is equal to 2x plus d. And the next thing, what we want is actually we want to measure, so O is our origin, the center of the image, and it's always useful to write your coordinates in terms of that. So what we're going to do is we're not interested in AC, we are interested in the distance of A from the origin, so we're going to simply subtract this x is compared to where our image, we're actually considering the image of what's being imaged. So you can see actually, just like Vermeer's camera did, it flips the image over, right? So this part of the image is being imaged on this side of the film, and this part over there is being imaged on the other side. Okay, so we simply use this definition of what AC is, and we're left with 2x plus d minus x. And so this is x minus d, and this OB to this distance is then once again BC minus x. We substitute in what we derive BC to be, so that's simply 2x minus d minus x, and this is x minus d. And so when we actually are imaging this thing CX, the image on your camera, what is recorded is basically the integrated light intensity. In other words, the integral over all the possible light that comes from the image from here to here is being concentrated at that point. Okay, and so we can write it like this. So the image C of x over there is simply the integral from x minus d to x plus d of f of s. Okay, so clearly what is being recorded here on our eye retina or the film or whatever is not the original image. Okay, we can write this expression, and the reason I'm going to write it is because it actually gets closer to the general expression. We can write this expression as the convolution of f of s with g. Okay, if you go back to our very early convolution example, where g is simply 1 if the absolute value of x is less than or equals to d and 0 otherwise. So you can work this out quietly, but what I'm saying is you basically have that this thing is equals to the convolution of f of g, and in this particular example, g is simply equals to that. So the amazing thing is that this formula, c of x, which is equals to the convolution of f star g, is always true. If you have put in a lens over here, you're going to get another expression that looks like this. G just changes. If you move the screen closer to the camera, which is more realistic, you're also going to get the same expression that the light intensity is equals to f star g of x. Okay, if you distort your camera's lens or distort the CCD chip, you're going to also get this. The most classic example, I don't know if you guys know these GoPro cameras. Okay, they have a fisheye lens. In other words, they don't just look forward like that, they look all the way around. But the resolution on the edges is not as good. That image is also related to the actual thing that's recorded on your picture with your original image convolved with something. Okay. And so this expression that C of x is equals to f star g of x is true for absolutely any lens, but g just changes. Okay, so in our derivation, g was pretty simple because our camera structure was pretty simple. If g is a lens, for example, what it's going to do is it's basically light's going to come in and it's going to focus it more accurately to a point. And so the image is going to be closer, or C of x is going to be closer to the original image, but it is still going to have this mathematical formula structure. And so the question now is, whenever you have an image, you always want to get back what your original function was. How do you do that? Okay, so this form of Cx equals to f star g is true for general cameras with lenses. In that case, very often, g of x is at least an unknown function. Okay, and it's dependent on the lens and where the shutter is and things like that. Okay, and this function we call the transfer function of the camera, right? It's a function that's dependent on the method you're imaging. If you're imaging with an X-ray thing, it also has a transfer function. In fact, that transfer function, you make a lens also out of very special material. And sometimes the transfer function actually changes with frequency, right? Certain lights, you work out your lenses that it treats all frequencies the same, but you know what a prism is, right? So if the light goes through, sometimes you put the light through glass, it can spread it out. Some cameras actually have problems like that where it splits the light into its different constituent frequencies, and each frequency has a different transfer function. Okay, we actually see that quite a lot in radio astronomy, in a way. There, that transfer function is frequency dependent. Okay, but for now, let's just assume it's not. You can always write it like this. And a very big question is, how on earth do you get your original image back, or a real rendition of the image back, if you don't know what G is? Okay, so basic fundamental formula for getting your light intensity onto a photo. For a perfect photo, old Vermeer wasn't too far off. The perfect photo is where what you record in your image is actually F. What should your transfer function be to give you that? Okay, we've just introduced him, and that's the reason I introduced him. What function, if you stick it in there, will give you F back? Dirac Delta function. Right, so if your transfer function is simply the Dirac Delta function, then you're going to get your original photo or your original image back. Okay, simply since the convolution of F with the Dirac Delta function is the function itself. And this is what Vermeer, with his little tiny, he had a very special pin to prick his curtain, was doing. It was basically just, if you want to actually look it up for just interest's sake, it's your pinhole camera idea. Okay, the problem here is that because the hole's so small, the light intensity is weak, so you have a dwarf picture, or a not very bright picture. Okay, the wider G gets, in other words, the more it departs from being a perfect pinprick, the more blurred the photo becomes, and in some sense that's obvious. You're integrating over light emitting from several parts of your image. Okay, and this is life. Apertures have a finite size. So the question now is, if the image is blurry, can you sharpen it? And the answer, amazingly, is yes. And that's where the convolution theorem comes in. And it's very, very clever, and it's a lot of people have, well, it's used a lot. Okay, so the answer is yes. Okay, the next question is, how exactly do we do it? And the how comes in with the convolution. So remember now that our convolution theorem, what it did was it said the Fourier transform of our image is equals to, and the image is the convolution of F and G. okay, is equals to the Fourier transform of G multiplied by the Fourier transform of F. So in the Fourier space, the image's transform is simply the product of the part that comes from the actual transfer function G and the part that comes from the image. And so, and this is just writing it out in a different way with a U argument. And so if we know G or its Fourier transform, in other words, we know the transform function, which we don't always know, but if we were to know it, then we could go and reconstruct the image, because we could find the Fourier transform of the image, which is just, the Fourier transform of the original picture, which is just the Fourier transform of the image divided by the Fourier transform of the transfer function. And we can then take the inverse Fourier transform of this combination and we have our image back. Beautiful, very simple. This is done often on computers. In fact, we're going to do it. But the problem over here is we want to, and so we can always do this, provided the initial assumption was that we know G or its Fourier transform. Okay, so if you know G or the Fourier transform, then you can get your image back and you can use the convolution theorem. The difficulty with this is always, how do we get to know what the transfer function actually is? Okay, just semantics. This process that we call, where we do this, where we take the inverse Fourier transform or the Fourier transform of the image divided by its transfer function, is called deconvolution. Okay, and one thing what happened was they shot up the original Hubble Space Telescope. They shot up, and somehow in the launch or somehow in the manufacturing, they'd made a mistake with their base mirror. It moved or it sagged. And so what that happened was they shot this multi-billion-dollar machine up, and the image they got out were worse than the telescopes on the ground. Okay, very embarrassing. And then there was a bit of desperation. They didn't let the public know what had happened. They had their little physicists go on and say, can we make a plan to at least try and save this, because otherwise we don't get money again. And so what they did is they wanted to they actually did deconvolution to try and fix the lens. Because in order to fix the lens properly, they eventually did send a mission to actually put a new add a correction plate to fix the lens. But before that, to get the first few images out, they wanted to deconvolve the image. So they basically knew mathematically they had this idea. The problem was, how do you get G? Okay. At least mathematically, there's a way to get G. Okay. Can you see it? If you want to get G and you go back, all you've got is your image. Okay, so you can always record the image. If you want to get G out, remember the perfect transfer function was a delta function. Okay, but we know it's not that. If you want to know what your delta function is, what you can do is, if you take an image of a delta function, then the actual image you see will be your transfer function. So if you are able to find some point source that behaves like a delta function, then, and you get an image out, then that in fact is your transfer function. So what the Hubble people did is they took an image of a source that they thought was completely point-like. In other words, they took an image of, I think it was a quasar, very far away from the telescope. They were pretty convinced, because they knew some of the physics, that it wasn't a galaxy or anything else fuzzy. And then they had a point source. They took that image and they assumed that it was the transfer function. Then they took the Fourier transform of that transfer function and they divided all future images by it and did the inverse Fourier transform, and that's how they fixed the problem, at least temporarily. Okay, so very, very clever. So the question is, how do you obtain G? And the answer is, take an image of a known point source. So you've got to be sure, because the image you're going to get is blurry, you've got to be sure the thing you're taking the picture of is a point source. And if that is so, then the image will simply be the delta function with our transfer function, convolve with the transfer function, which will simply be the transfer function itself. So it's very, very clever, and most camera calibrations, initially they do that. They develop the CCD chip, they put it with a lens in front, and then they take images of point sources, and they see what image they get, and then in the software they go back, and then they say, this is actually a point source. Let us, all our future photographs, we're going to deconvolve using that image. Okay, so that's what they call camera calibration, and it happens a lot. Like, so in the Karoo we have the Meerkat telescope. What we also have there is another experiment that's actually entirely South African run, that hasn't got a whole bunch of foreigners using our data. That telescope is called Hyrax, basically a DASI. It's got a different frequency regime from the Meerkat telescope. And they also have to get the images out, and they also have this problem that the actual antenna are very, in some sense, rustic. They just look like a whole bunch of, because it's low frequency, you don't need a very accurate, very well machined telescope. But the problem is they want to now know how to make the image accurately. And what they do is they have got a drone up. So they actually have a drone that gives off radio waves at that frequency. That's a perfect point source. And so their first experiments is not to image the sky, but they image the drone. And they, because they know it's a point source, they systematically build up this convolution functions for all possible positions of the drone, so that when they look at the sky, they can use that to get actually the image out. Okay, so that's the calibration, and it's way fun because I watched the emails with the drone operators saying they had this difficulty, or it's not easy, but it is possible. And so this is what they're basically doing. They're building up their transfer function. If you have an X-ray machine or that's my sister does chemistry, and they do a lot of diffracting with crystals, which is just a different, you're actually not imaging the crystal, you're imaging its Fourier transform. But when they do a very similar thing where they actually have a source where they know precisely what it is, and then they do the experiment on it, they look at the result, and because they know what the result is, they calibrate the machine. So, or they basically calibrate the imager that takes that round photograph, so that they can then accurately, for all other unknown pictures, then deconvolve it and actually get the image out. And we're going to do a couple of these, I think like in a week's time, where we actually do the problem ourselves. We use this type of thing not only for getting clear image out, but actually also for blurring it, because sometimes you don't want the smartest image or the clearest image because it shows all your wrinkles on your face. So a lot of the touching up of cameras and stuff is actually blurring a otherwise perfectly fine image, and selectively blurring it, because actually it changes your focus. Like, it's one of the things when you do cinematography, sometimes you have like a love scene where the two like meet each other, and then what the producers usually do is they basically put a filter on, and we're going to do this. They blur out the whole of the background, that your focus is on the scene of interest. So all those techniques are also possible, but it's exactly the same idea with this convolution theorem. You simply do things to the Fourier space, and then you take the Fourier transform back. Okay, so let's just go back to our very simple camera image, okay, and just check that our idea works. And suppose here again remember here was the picture up at the top, and then halfway in between you had this thing that was acting as sort of a block of the image, and then here at the bottom you had your CCD camera that had the image, and this distance was D, okay, the opening of the image. And so if you have a point source up here, what you're going to get back is simply this thing is going to shine through here, so it's going to open up, and because this distance are the same, it's going to be D from over here and D from over there. So your image of a point source, excuse me, in our very simple example is simply going to be 1 if x is between 0 and D on the positive side, and 0 and minus D on the other side. And so if you actually write that out, G is simply going to be 1 if the absolute value of x is less than D, and 0 otherwise. And this was exactly the convolution or the function we used in sort of motivating this expression originally. Okay, sorry, no, that expression originally. So it just confirms at least that our picture is consistent. All right. So that is that for image convolution. Okay, questions about this? So then now I've got your problem set. Let me just get it. Let's discuss it a little bit. Okay, I'm actually going to stop this.